Hello everyone and welcome. Today we are diving into 3D integrated circuits, a topic at the heart of modern computing, and why vertical stacking is hyped as the path to near unlimited performance. The real question is, if we can keep building upward, why can we achieve infinite bandwidth? And why does the real world hit a hard wall? In this talk, from a circuit designer's perspective, I will unpack the engineering trade-offs and design tricks that set the principal limits of 3D bandwidth. Let's get started. To understand the limits, we have to appreciate the promise. For decades, chips were 2D and all data enter and exit through the edge pins. 3D IC flip this with area I/O, letting us press thousands of vertical TSV connections across the die, so links are extremely short. Resistance and capacitance drop, performance arises, and energy per bit falls, which is why for AI and data center chips edge bandwidth density becomes the most important metric. Here, we hit the first hard wall, a circuit level constraint set by the power density budget, stating multiple active dies multiplies local power. Heats become trapped in a heat sandwich, and that creates a firm design limit where interconnect and circuit can consume only about 2 watts per millimeter square before risking thermal failure. This budget governs every subsequent choice, preventing us from simply running all circuits at maximum speed and explaining why bandwidth is not infinite. Power delivery intertwines with thermals. A 3D stack is a skyscraper whose PDN must carry Kx current through the limited vertical TSVs, creating IR drop, so upper dies see lower, noisier supply rails, and the real killer is electron migration, whose rate accelerates with high current density and temperature. Try to fix IR drop by adding more or wider power DSV increases dual heating, which raises temperature and further accelerates EM, degrading the very PDN you are trying to protect in a vicious feedback loop. Even with a wide and slow approach, we face signal integrity limits. Densely packed TSVs coupled at GHz can cause crosstalk. The standard migration is GSG shielding, which cleans the signal, but consumes area because ground vias carry no data. More advanced receivers can cancel roughly 70% of crosstalk with kernel techniques and precise termination, but they add analog capacity and delay match clock forwarding, yet robust timing only if the clock path exactly matches to the data path. Every trick has a trade-off. To push bandwidth without more wires, simultaneous bidirectional SPD signaling sends data both directions on the same wire at the same time. Each transmitter also drives an inverted replica locally, and the receiver subtrates its own outgoing replica from the mixed line signal to recover the far-end data. It's elegant, but demands complex analog subtractor and replica paths, burning area and power, and it's not yet standardized in interface like UCIe, showing how costly a simple 2x can be. The winning 3D playbook prioritizes energy efficiency over per wire speed, abandon power-hungry 16:1 series used in 2.5D meant full use of the 37x pin count increase to build massive parallel interface and use simple buffer over low ratio serializer with DDR over just buffering a 2 or 3 gigabit per second per lane. So total bandwidth only rise by 1.5 while staying under the power density limits. The bottom line is the power density prevents over data density. So 3D multiplies connection, but never overturns physics. Here are the summary images showing you why 3D IC hits bandwidth density wall. The dream of infinite bandwidth is bounded by 2 watt per millimeter power density budget that forces an architecture speed. 2.5D is narrow and fast with a complex series, while 3D is a wide and slow with simple parallel links. Circuit tricks like crosstalk cancellation and SPD can stretch limits, but exactly cause is complexity, area, and power. And the only viable path for dense 3D is optimizing energy per bit rather than speed per wire. Because in the end, bandwidth density is constrained by power, thermal, SI, etc. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video with the people who may be benefiting from it.